I'll talk about some surfaces which remind projective planes and their homological properties. So first, let's start with CP2. So what is nice about this surface? First of all, it has the minimal possible cohomology. So it's three-dimensional space. It's the minimal space for all surfaces. And second, which is related to this one, is that derived category of coherent sheaves on CP2 has the simplest possible structure. It has a full collection. So it has a full exceptional collection. Let me recall once again what this means. The definition, which goes to Bondel-Orlov, is that if X is a smooth projective variety, and we have a sequence of, let's say for simplicity, of vector bundles on X, then this sequence is called exceptional if it's orthogonal in some way, orthonormal in some way. So E1 to ER is exceptional. Right, so if, first of all, each object is exceptional, which means that the X algebra, for each I, the X algebra is generated by the identity. So it's C in degree 0. There's only identity and no higher X. And second, if there's no Holmes or X backwards. So if X from EJ to EI is 0, where J is bigger than I. So this is an exceptional collection. It's a little bit like a basis, and then, so like a linear independent system, and then it's called full. So moreover, so, right, so, and then E1 ER is full if in addition these guys generate the derived category of coherent sheaves. So E1 to ER generate dB Koch of X. So explicitly, this means that any coherent sheaves has a filtration with quotient of these kinds. And strictly speaking, generate means that the smallest triangulated subcategory of this, which contains these guys, is the whole thing. Right. Okay, so then the first example of such thing was given by Beilinson, was a projective space. So the theorem of Beilinson is that CPN has a full collection which is given like this. So O01 up to ON is a full exceptional collection on CPN. So let's think a little bit what this means. First, exceptional means that there's no, so each object is exceptional, and that's automatic here, but more importantly, there's no X backwards or Holmes backwards, which means here that the sheaves O minus J, where J is in between minus, so when J is between 1 and N, are acyclic, which is known to be true for CPN. And then fullness is a little bit more tricky. Okay, but in particular on CP2 have this collection, and today I'm talking about surfaces which have something similar to CP2. Right, so how close one can get to projective plane? First of all, there's a theorem of Yau that if S is a compact Kähler surface, and S is homotopy equivalent to CP2, then S is the same as, so S is isomorphic to CP2. So in particular, one cannot deform complex structure or cannot, right, so one cannot get too close. But then on the other hand, right, this was maybe 77 or 78, and then Mumford gave an example of the following thing. So maybe it's 79 or something. He constructed a surface which gets to CP2 as close as possible. So S, right, so smooth projective surface. Of general type, which has the same cohomology as CP2. So dimension of cohomology of S is 3. So of course, if this is the case, then the Hodge diamond looks like 1, 1, 1, 0, 0, 0, 0, 0, 0. These threes are always, this 3 is always there. Right, so, right, and these surfaces were called fake projective planes, such as
the example of Mumford is one surface or several surfaces?
Mumford is one surface, and but then Mumford build them over QP bar, so it was a very complicated construction with p-adic uniformization. But then I'll tell later that people classified this. So Mumford had a very exotic construction with p-adic, so over p-adics.
Nowadays there are plenty.
Yes, there are 50. I'll talk about that. Or 100. Right on. Right. So.
Structure of the cohomology is different.
No, it's the same. It has to be the same. It follows just from Poincare duality that yes, it's the same. Right. So okay, let's deduce first some proper. Yeah, right. Let's. You're right. So did you mean? So yes, it depends on what you ask. As I'll explain later, over Z the cohomology cannot be the same. There will be torsion, but with rational coefficients, it's exactly the same as CP2, or with complex coefficients. Right. Okay. So yeah, formally it's right. So for surfaces, all the numerical invariants are related. So it's easy to see that these 3 ones imply that the canonical class squared is 9. So as the same as for CP2. Right. So what else can we say a priori is that second right. So okay. Right. Yeah. Assume project. Yeah. Assume. Yeah. I guess for surfaces there's not much of a difference, but I normally think of projective, smooth projective. Right. In particular, Kähler. Right. So we can say something about Picard group. In fact, the first Chern class mapping to the second cohomology is an isomorphism because the kernel and cokernel are given by these 2 zeros. Right. Also, because it's one-dimensional here, this will be Z plus torsion. This is finite torsion, which will appear later, which will play an important role later. Right. And finally, it's a very interesting open question about 0 cycles on S. It's supposed to be, again, given by degree to be Z, but it's not known. And it's the Bloch conjecture. Many people try to prove it, but it can somehow never work.
Big open question.
Yes, it's a big, yeah, right.
Yeah, but even this, absolutely no idea.
There are a lot of surfaces, fake delta surfaces for which Bloch conjecture is true.
Yes, I know, but for this specific one, yeah, people have no idea.
Right, and the reasons that, yeah, right. The reasons that the construction is very not explicit. Yeah, yes, and therefore it's hard to prove anything about this. Yes, not algebraic, right? So if we had a surface which is covered, let's say, by product of two curves, then it's automatic. But for right, so how does the modern construction go? It goes as follows. So S is a quotient of a complex 2 ball by a discrete group. So B is a unit ball. Then on B, there's a group PU21 acting. So it's the subgroup of PGL3, which preserves the 2 ball. Right, and then one can take gamma inside. Right, so one can show that all fake projective planes are such quotients where gamma is arithmetic, torsion-free, co-compact subgroup. All right, so torsion-free will imply that there's no fixed point, so it's a non-covering. Co-compact means that the quotient is compact, and arithmetic will imply that one can classify all such things. Do you have a question? No? Okay. Right. Okay, yeah, so finally, all such gammas were classified by Prasad and Jung and Cartwright-Steger. They gave a complete classification for these gammas into 50 isomorphism classes. Sorry? B is a complex manifold as well as a real manifold. But it's open in C2. It's not a sphere, it's a ball. Open subset. Complete classification. Into 50 isomorphism classes. So I won't tell about this. It requires some arithmetic data, like a number field, a couple of primes, their algebra over in this number field, and then they construct such a thing. Right, and in particular, Cartwright and Steger finished it on the computer, so there's on their website plenty of computer codes with for each of the subgroups. Everything can be computed about it. Right, so now, yes, as Sergey already mentioned, for each of this group, there are two surfaces so there's B mod gamma and B mod gamma bar. Turns out that they're never isomorphic, and so it means that there's no real model, right? And right, so there are 100 fake projective planes. Okay. Right. So now let me give a table which compares geometric property of this S and arithmetic properties of gamma. Right. So gamma is here. S is here.
Is that number 100?
Yes. Yes.
How do they classify the subgroups? Or is it only arithmetic subgroups?
So first, yeah, it's known that they are all arithmetic, and then, but
how you know it is arithmetic from fake project?
I'm not sure, but it's this, yeah. So for surfaces, it's kind of theorem of Klinger and Jung, from
Oh, for arithmetic itself.
So what do you mean? How do you know it's arithmetic?
But how you obtain proven fake projective that the subgroup is arithmetic? There are many non-arithmetic subgroups.
Yeah, honestly, I cannot tell you this, unfortunately. Right, so, but once you know the arithmetic, computer program is used to classify, finish the classification. Okay, so pi1 of S is gamma itself, simply because universal covering is B. Then first homology group is abelianization of gamma, so gamma modulo the commutator. Right, then cohomology with any coefficients, in fact, they correspond to group cohomology on this side. Right, so what else there is? There's automorphism group, which will be important for us. Automorphism group is normalizer of gamma mod gamma. So we have to look which automorphisms of PU21 descend to B mod gamma, and this is this one. Yes, which elements, yes, right. Yeah. Little like Galois theory. Right, and then finally,
So it's like Weyl group, yeah?
as if you say so, yes. Okay, quotient, you mean quotient, yes, like, no. Right. Okay, so now finally the last thing I want to say is let's look at this one. So let's ask what is the index. So is Ks divisible by something or not? So if since it's 9, and if Ks is divisible by R, then R must be 3 or 1. So, right, so we can ask whether Ks is 3H for some H. Can it be anything else than 3 because it's 9? And this corresponds to the fact that gamma, which is sitting in PU21, actually lifts to SU21. So gamma lifts to SU21. So that's what it takes to descend O minus 1 from the ball to the quotient. It means that, right, that O minus 1 must be linearized.
What about H? Is it 10?
Yes, of course, because Ks is ample, right? So
Oh, sorry. Very.
no, it's not very ample. Neither Ks is very ample. They have no sections. H has no sections. Ks, I will show.
And which power is very?
Yes.
I just now realize that this is SU21, but yeah, exactly SU21. So this means that the Hermitian form is sum of 2 squares minus
Sum of 2 squares of modulus minus third one. And that's because the complex ball. It's related to the complex ball.
Group of isometries of complex hyperbola.
Mm-hmm. Yes, it's not very important for, but I mean for the talk, right?
I didn't understand. I mean the last statement about this gamma. So we have a 50 gammas, and when we have this lifting
Almost in all cases. So it doesn't always happen. So it's not automatic, but almost in all cases it lifts.
Almost in all cases for 50.
Maybe 48 or something.
Okay.
So, or 47.
46.
So.
Half and half.
Okay, right. So let me also make remarks about what is this equal to. So it's important for us that this is never 0. So in fact, it follows from the cohomology. It's always finite torsion.
You mean it is never Z? H has 0.
So right. So it's always finite to always non-zero finite torsion. So there's no conceptual explanation for this. It follows from the classification that for each these gammas. Right, and therefore integral cohomology is never the same as for CP2, right? And it's the same T, so universal coefficient theorem implies that it's the same T here. So torsion in H upper 2 is the same as torsion in H lower 1. What? Isn't it what? Okay, they're uncanonically isomorphic, right? Not canonically isomorphic. Okay, then this one. It's a small finite group. It can be like just one, Z mod 3, Z mod 3 squared, and the case which will be interesting for us, G21. It's the group of order 21, which is not abelian. So unique non-abelian group of order 21. it's a semi-direct product of Z mod 3 and Z mod 7. Right. Okay, so then, as I said, this happens almost always, and this thing happens for 3 groups. So we'll prove something for 3 groups. Okay. Right, so now I state the theorem. Theorem is this. So first, a fake projective plane S never has a full collection. So a fake projective plane S does not admit a full exceptional collection, which means that there can be no exceptional collection which generates the category. So second, if automorphisms group of S is G21, so we're in the last case, so that's six planes like this, then O minus 1, O minus 2, sorry. First omega S is divisible by 3, so it has index 3, so we are in this case. And similarly as for CP2, O minus 1, O minus 2 is an exceptional collection on S. So we divide canonical class by 3 and take these 3 things.
There is a torsion, and that what means O1. There is a torsion in Picard.
Right, in this case there's no 3 torsion, right. In this particular case there's no 3 torsion.
Okay.
So yeah, it's uniquely defined. Right. Okay, so let me say a few words about the proof, and then I give some remarks. So the first thing follows basically from existence of torsion in S. So as I already explained,
Maybe you will say what is the torsion in this case?
it's some finite. They're not quite meaningful. They are finite abelian torsion groups. Yeah. Okay. Let me explain this. Yeah. So, sorry, I forgot to say that all of this is joint work with Sergei Galkin, who is present here. Right. So, in particular, he came up with this nice argument that if okay, so let's start with torsion in H2, right? So as I already explained, Picard of S is the same as is isomorphic to H2 of S, and this so this is Z plus torsion.
But anyway, the question: what is this torsion? Do you know it?
Yes, we have a table. But these are some small groups like Z2, Z3, Z4, Z5. Yeah, okay, this has no Z3. I can show you table.
This is Z not to Z to the power 3, 4, or 6.
Right, so it's only 2 torsion. Yeah, for this case, it's only 2 torsion. I can show you later the whole table. Right, so, right, and then one can show that K0 of S also has torsion. This is basically follows from careful application of Riemann-Roch theorem without denominators, that if Picard has torsion, then K0 has torsion. But then this is an abstraction, because if there's a full collection, on the other hand, if S admits a full collection, then K0 of S is free abelian group of finite rank, of the same rank as the length. So of rank R, if this is of length R, this is because Grothendieck group is invariant of the derived category, and it's additive for semi-orthogonal decomposition. Therefore, each object gives you one direction, and if it's full, there will be nothing else. Okay, so this was the first. So it's tempting to say that these fake projective planes have a full collections up to torsions, something like this, but it's hard to make it precise. Right, and then for second, we need to prove that this 3 is an exception collection. So we need to prove some vanishing of X groups. So it's an exercise in homological algebra, which we now can do. Right, so we need to show this, that cohomology of O1 and cohomology of O2 are both 0. So that's what we need to show. For CP2, it's -1 here and -2 here, but that's exactly what happens. So all the signs get changed when one passes to fake projective planes. Okay, I'll make a table with all these groups.
Can you explain?
Yes. This is what we need to show. Yes, even H0, right? So they are acyclic. They have no H0, no H1, no H2. Like for CP2, O-1, O-2 are cyclic. Okay, so the table will be this. So I'll compute H0, H1, and H2. And here we have these sheaves. So what do I start with?
So you put H0 on the top.
H0, H1, H2. Okay, let's say O, O1, O2, O3, O4. Right, so some of the entries are straightforward to fill in. Namely, if a structure sheaf has 1, 0, 0, because these are the Hodge numbers. And also because this O3 is omega by assumption, we can say that these are also known and they are 0, 0, 1. And this matches CR duality, which identifies kind of it, which is symmetry with the center somewhere here. So this one corresponds to this one and so on. Right, what else we know vanishes now? This is 0, because if we had a section here, we take a third power and get here, which is 0. Right, therefore, by duality, H2 of O2 is also 0.
Why does 0 again?
This one. Because if we had a section here, we take it 3 times, we get a non-zero section here, and there's no sections here. It's tempting to say, therefore, this is also 0, but then it would be done. But it's not quite. Doesn't look so. Doesn't look like it's sufficient that this is. Right. So now we have. What else we can use? We can use Riemann-Roch. Riemann-Roch tells us in this case that Euler characteristic of O of I is I minus 1. Yes, times I minus 2 over 2. So if you recall, on CP2, it's plus here and plus here. So at least when I is 1 and 2, these are candidates for being completely acyclic because they have no Euler characteristic. Right?
So it is enough to have one more vanish.
Yes, right. So if I write this delta for this one, then because this vanishes on this and on this is also delta. And then by duality, I have the same two numbers here. So we'll need to argue that delta is 0. And it's not quite trivial, even though it looks kind of obvious now. Okay, but we can compute the rest, actually. The rest is easy, because the rest is very positive. Kodaira vanishing tells us that if a bundle is more positive than canonical class, it has no higher cohomology. Therefore, I have 0, 0 here. And this number is computed from this formula, which is 3. So, and so on. The rest is easy. And then also here, it's easy because now by duality, we know all the values here. So it will be 3 here. Okay, now what can we do about delta? we can compare sections here with sections here by taking their squares. Unfortunately, this is not 0, but still we can give estimates on delta. Okay, so note that so far I haven't used the G21 action. This is very general. So if we know for a given S vanishing of this thing, then it has a collection. And for G21 action, we'll prove that this is 0.
Do you know how does it act on this three-dimensional space?
Yes, this will be this will be the proof, right? Okay, so we have what we'll use is this map from the global sections of O2 2 times to global sections of O4. And one can estimate the image of this. The image cannot be too small. So in particular, this is 3-dimensional. It will show that this shows that delta is no more than 2. One can make this computation. See if there's more than 2 sections, then there will be too much here. Okay, so this delta is 0, 1, or 2, and in this case we prove it 0 as follows. We again use the same morphism, but now take into account G21 action on both sides. So now we not just have vector spaces, but G21 representations.
So you already assumed that this is G21?
Yes, yes. So in the second, yeah, I assumed it from the beginning, but I just haven't used it for now.
For the rest, it's just not true? Okay.
We think that whenever k is divisible by 3, this delta is always 0. But we were not able to prove it, unfortunately. Okay, but now if this is the case, then all the cohomology of these sheaves are representations, G21 representations. In particular, we can, yeah, this map will be G21 map of the representations.
But this map is also symmetric, so you can write S squared instead of 4.
Yes, that's right. I could write S squared. Right, and then we prove that this is irreducible. This is a reducible representation. By computing characters and knowing the character table of G21, one can figure out which representation it is and turns out to be a reducible one. But then we are done because this group has no 2-dimensional representations. It only has 1-dimensional, 1-dimensional, 3-dimensional. And since this delta is 2, 1, or 0, this is the sum of characters. Therefore, this thing is also this is the sum of 1-dimensional representations. No, it's not obvious. You're right. It's not automatic, but it is in the case that O1 is linearized, can be linearized in this case. And in this, we rely on computer programs by this guy, unfortunately. So it has to do also with some lifting of this arithmetic. Okay, right. So, and since this is a sum of 1-dimensional representation, this 3-dimensional irreducible, this map must be 0, and therefore delta itself is 0.
Why, if this value is 0, you conclude that this is 0?
Because if you had a section, you take it 2 times, it would be a non-zero section here. But if the map is 0, the section forced to be the same, yeah. The same as y, this is 0, yeah. Okay, right, so now in this case delta is 0, and therefore what we get is an exceptional collection. Right. Are there any questions so far?
First, why don't you try to use projective representations instead of, I mean, G21 obviously acts on this projective case. There is a projective representation of this group.
You mean if we take projective space, projective?
No, projective, I mean, PG, it acts on the projectization of these vector spaces.
Okay.
So this is sort of obvious without any computer computations. It wasn't written
No,
up.
no, it's not obvious. Because it can send the line bundle to another line bundle.
No,
It's automorphism group, it's so I mean that
if you preserve the degree and there is just one bundle of given degree.
no.
No, but that's
Because torsion. There is a torsion in Picard group.
Ah,
It's not true.
It is 1/3 of the canonical class, and this one is unique. In this case, there is a unique bundle, which is
Yeah, it's
1/3.
No, so in this case, there's no three torsion. Well, we can talk about it if you have some idea. We thought about it for a long time, and I think we need this, that this O1 is linearized. I think somehow, otherwise, let's talk about it afterwards. Okay, right. So some remarks now about phantoms. So we have an exception collection which is not full. So what do we do about it? We can take the orthogonal complement. So okay, a corollary of the theorem is this. So let S again be a Fay projective plane with G21 action. So then we can say that the whole derived category of S decomposes as follows. So we have three exceptional objects and a category, some category AS, where AS is so-called H phantom, which means that its Hochschild homology vanishes. And so I'll write everything and then I'll explain how this goes. And moreover, we can do this equivariantly. We can take into account subgroups of G21 for G as any subgroup inside G21. We can decompose derived category of equivariant coherent sheaves. So what is this? These are coherent sheaves of S which are linearized for G. And this has the following shape. So each of the exceptional objects is multiplied by representations of G. So taken as many times as there are reducible representations of G. And then the third one and finally, there's again the orthogonal, which I denote AS upper G. And what can we say about this orthogonal? So it's again H phantom, and moreover, if the quotient S by G is simply connected, then this ASG is also a K phantom, which means that its Grothendieck group is 0. But we know it in all cases, no, for the quotient.
No, for Z mod 3 not always. Just depends on G. G is divisible by 7.
Okay, but it, okay. And we know Bloch conjecture for S mod G. So K phantom means that Grothendieck group is 0. All right, so how does all this go? So the first lines are more or less obvious. So it follows from work of Bondol-Kapranov a long time ago that if there is a exception collection, then one can always take its orthogonal, and there will be a decomposition of this kind. Collection plus the rest. Then the second line, it's also kind of obvious. Yes. This is the definition. H star of. What? This is this. Yes. So phantom means that it's 0, but not 0.
But the category is not 0.
What?
But the category is not 0.
Yes. In each of these cases, the category. Yes, right.
You should consider 0 as a phantom.
Yeah.
It's a bad.
So let me comment that this complement in the second line is automatically an H phantom. That's again follows from, so yesterday we've seen HKR theorem maybe several times. This basically says that cohomology of the variety can be extracted from its derived category. So this is the statement that H upper star of any variety, in fact, is isomorphic to Hochschild homology of its derived category of coherent sheaves. So there are some problems with grading, multiplication, and the rest, but as vector spaces, these two have the same dimension, right? Z2 graded, okay, right. As Z2 graded, no. Right, but then also H lower star is additive for semi-orthogonal decompositions. Therefore, once we have the decomposition, each exceptional object gives rise to one copy of C, and then there will be the complement, which is H lower star of AS. So this is a standard argument. And then on this side, we have C cubed because it was a fake projective plane. Therefore, this must be 0, right? So this was the first thing. Then this kind of descent to equivariant category is also more or less standard. That's because these line bundles are linearized, and therefore it's known, let's say, by the work of Yelagian that then the equivariant category have this shape. So each object is taken twisted by each representation of G. This will be a collection, and then again, by definition, this is the complement. And similar reasoning, which involves some counting of dimensions of this cohomology of this quotient, shows that this is always an H phantom.
And how do you compute the function homology of the equivariant category?
That's a good question. So we think that it's always the case that if we have H phantom with a G action, then the equivariant category is also an H phantom, but we are not able to prove it.
Speaking about DB code, so how do you compute equivariant?
So there are several ways. There's orbifold cohomology computation, and we can know how this is related to resolution and so on. For surfaces, it's...
Probably you should know how many fixed points.
Yes, and yes, this we know, of course, yes. We know everything about the action of G21 on S. For each subgroup, there are 3 fixed points. So for each cyclic subgroup, there are 3 fixed points. Right, and this K phantom is a little bit more tricky, but it goes along the same lines that simply connected implies that H lower 1 of the resolution is 0, and therefore, together with Bloch conjecture and Riemann-Roch without denominators, it implies that the Grothendieck groups of surfaces of this kind are free, and therefore, once we have the exact number of exceptional objects, they will span the whole Grothendieck group. So the torsion, which was an abstraction before, is not there, and there's no abstraction. So
but this is, in these arguments, you pronounce Bloch conjecture. So once again, It's not an absolute statement. This statement model.
No, I think it's confusing. No. So for those cases we need it. Okay, I think you're confusing the audience now. That for the cases we need it, we know this thing. So when it's simply connected, we know the Bloch conjecture because the quotient surface is simpler than it's an elliptic surface, and then it's known by the work of Bloch, Kast, Lieber, Anderson. But then we don't know it's simply connected. When it's not simply connected. Okay. Right. Okay. Yes, I think I'm. Okay. Final remark is that similar statements are known.
Can I ask why you know that this equivariant category is non-trivial?
Because we can produce an object there. Okay. If we have an object upstairs, we take its orbit downstairs, it will be non-zero. Right. Or maybe one can use this Sasha's height to show that the collection is not full. Okay, fine.
And this quotient S by G is, you said that it's elliptic surface?
Yeah, I think so, yeah.
So this means that this elliptic surface, and you take a resolution of singularities, and you get that this elliptic surface has a exceptional collection of maximal lengths.
Not quite. We do equivariant. So yes, so there are equivariant category and there's the resolution. Equivariant is a bit bigger and work with this one. We don't make a statement about the resolution.
So the singularities are not canonical, yes?
Yes.
Okay.
Yes. So it was G21, so it's Z mod 3 and Z mod 7. Z mod 3 acts in SL2 and Z mod 3 acts like... right. Okay, final remark is that there are known other fake Del Pezzo surfaces, for example, fake P1 cross P1, where these statements are also established that derived category reminds derived category of the corresponding Del Pezzo, but because of some torsion, for example, it's not full. Right. Okay, right. So I think I'm finished now.